You've probably all heard of acids and bases and the general idea of acid-base chemistry in your previous studies or just in day-to-day life. For example, I'm sure many of you have seen the rather tropey papier-mâché volcano science fair project with vinegar and baking soda foaming together and erupting out of the volcano. And you've probably heard the following argument for how it works. Vinegar, an acid, reacts with baking soda, a base. Although that's a pretty oversimplified explanation, we'll just go with it for now. But you've likely come to the conclusion that those two things, acids and bases, are opposites, and that when paired together, they eventually make something neutral. So what exactly makes an acid or a base a base? In short, it's the ability to donate or accept electron pairs or protons. Reminder, protons are positively charged hydrogen atoms or H+. When an electron pair moves, we're talking about Lewis acids and bases. And when a proton moves, we're talking about Bronsted acids and bases. Here are my dumb mnemonics to remember which is which. Lewis starts with L, like electron pair. And Bronsted starts with bro, which is pretty close to pro, like proton. I know it's a dumb trick, but it's worked for me for like 8 years. My second stupid mnemonic comes from, for Lewis acids, and it's Lewis acids are electron acceptors. From that, I can then make sense of the rest of the types. If Lewis acids are acceptors, then Lewis bases must be electron donors. A proton is like the opposite of an electron pair, so where a Lewis acid accepts electrons, a Bronsted acid donates a proton. And if Bronsted acids are proton donors, Bronsted bases are proton acceptors. Again, dumb mnemonics, but they work. For this chapter, we're going to focus almost entirely on Bronsted acids and bases, which are, again, proton donors and acceptors, respectively. This makes representing these acid-base reactions pretty straightforward. So I've drawn here HA plus B producing A minus plus HB plus, where H is the acid since it has that proton that it can donate, and B is the base because it takes on the proton. Notice here that I've drawn this as an equilibrium reaction, so there's not just the forward reaction going on, but also the reverse. And this is pretty curious because now, as I've drawn it here, the proton is donated by HB+, making HB+ an acid, and accepted by A-, the base. There's sort of a role reversal here, where HA is an acid and A- is a base, but the two are closely related. We describe this relationship as an acid having a corresponding conjugate base, so that when the acid donates its proton, we're left with its conjugate base. Likewise, the base, B, after accepting a proton, turns into its conjugate acid, HB+. Most of the time, we'll be looking at Arrhenius acids and bases, which are Bronsted acids and bases, just in water. Water is pretty cool for many reasons, and acid-base chemistry is no exception. Water, H2O, can act as both an acid and as a base. So, for example, when paired with a proton donor, we have this, where HA is a Bronsted acid and H2O is a Bronsted base. Vice versa, water with a proton acceptor looks like so. Now, B is our Bronsted base and water is a Bronsted acid. The conjugates to water in these two equations are H3O plus or hydronium and OH minus hydroxide. And these two reactions I have drawn here are the generalized acid and generalized base equilibria, meaning this is the standard way that chemists think about Bronsted acid and base reactions. This quarter, we'll have quite a few types of equilibria in our toolbox, and it'll be important to quickly recognize a reaction as belonging to a certain class of equilibria. In the two I have drawn here, the key indicators I note are that the acid equilibrium has hydronium in the products, and that the base equilibrium has hydroxide in the products. Partnered with these generalized equilibria are their generalized equilibrium constants, which are just the Kc constants for the generalized reactions. For example, the equilibrium constant of our acid equilibrium, let's call it Ka, is drawn as such. Remember that liquids and solids don't contribute to the equilibrium expression, so that's why we don't have an H2O term in the Ka expression. Likewise, the equilibrium constant for bases, Kb, is drawn here. Recall from the previous chapter that a large K value indicates a strong favorability for the products, and a small K value means more reactants are present at equilibrium. In the context of Ka then, a large Ka means that the acid, Ha, is going to strongly dissociate or break apart into its conjugate base, A-, and hydronium, H3O+. The same goes for Kb. If Kb is large, the base, B, is going to very readily take the proton from water, producing a large amount of the conjugate acid, Hb+, and hydroxide, OH-. In these situations where we have a large Ka or Kb, we refer to the corresponding acid or base as strong acids or strong bases. We'll talk more about acid and base strength, how they relate, and what factors affect their strength in later videos.